back. We are going to do chi-squared tests. And don't write this on the sheet, but has everybody taken, I think, bio? You did chi-squares in bio, right? Like at least a little bit.
Yes.
For proportions, you use a z-test. For means, you use a t. If you're dealing with categories, that's gonna, it looks like that. It's like the Greek letter chi, basically the x squared. You're gonna do chi-squared. So this is, what we're gonna look at is the AP world will claim that 20% of students get each score on the AP test. So if this is 100 people total, so you expect 20, 20, 20, 20, 20. That's like a little off from that, but is it far enough away that we'd be like, yeah, their claim is wrong, or is it close enough that you'd be like, yeah, I can't say it's wrong. So we're gonna look at, are these categories like evenly distributed? So I'm gonna do that example with you, and then we'll do a template, and then I think we'll probably have time to have you like try one also. So this is what's called, there's 3 different types of chi-squares. This is what's called a goodness of fit. Or in your calculator, just say GOF. And you know that you're supposed to use this test when you have one row of data. In the 2 other ones, you'll have like a table, kind of like a matrix, spreadsheet, grid, whatever you want to call that. But this is just like one row, and it could be vertical, horizontal, it's just a list of data. So HO is going to be the claimed distribution of AP stat scores. Is correct. So we start off assuming they're right. Like they claim that 1, 2, 3, 4, 5, they're all equal. 20% gets every score. I don't know if they actually claim that. I'm just making that up. I feel like it's more bell-shaped. Like it's harder to get a 1 and a 5 than it is. I don't know. Okay, so then HA would be like, I don't know which one, but at least one of those distributions is wrong. So at least one. Claim proportion. Claim distribution. Is incorrect. Last. For the conditions, it's a little bit different. There's not a center in a chi-squared because it's like intentionally skewed to the right, so we can't really do that. So I'm going to say IRL are the conditions. In real life, you get an IRL. We're here in IRL. I is independence, the same as it was before. Independence. That's the 10% thing. So 100, because there's 100 total in that list there. 100 is less than 10% of all AP Stats tests. R is randomness. I didn't really say, so we'll just say like assume SRS. Those 2 are normal. And then L is large counts condition. It's the large counts. It's not like a vocab where you have to know like large counts condition, it's just large counts. And what you need is the expected I guess just watch me do it. I don't know what to call this. So ones, twos, threes, fours, five. And what I'm going to do is put the actual and then the expected in parentheses. So leave room in your box because you got to put two numbers. So like I'm going to put 17 here, but then below it I'm going to put what the expected number would be. I'll get to that in a second. 20, 25. And then 20. Alright, so the expected, it kind of depends on the way the problem's phrased, but you're looking for like the percent of things that they say to match up with the percent of things that we do. That made no sense. Sorry. AP test claims that 20% go into each of these categories. There's 100 total people taking the test. So if 20% of 100 people are supposed to get a 1, how many people are supposed to get a 1? 20 people. You're just doing like, I expect 0.2 to be in this slot, times there were 100 people. 0.2 times 100 is 20, so I would expect this to be 20. So this is going to be 20, and you can just write 20. I'm just showing you this for like the purposes of teaching it. They say they were evenly distributed, so that would mean 1/5 goes in each slot. There's 100 people total. So I would expect that to be 20. Instead of 1/5, you could put 20%. You could put 0.2. Just getting at the idea that all of these boxes should be equal. There's 5 of them. There's 100 people, so they should all be 20. And those are the expected counts that are supposed to be greater than or equal to 5. That's this condition up here. And they are 20 is bigger than 5, so we're good. Alright, the chi-squared statistic is observed minus expected squared divided by expected. Probably going to get mad that I didn't do this first, but have you ever guys seen that E thing? Did you do that yet in pre-calc? The summations. Who's in pre-calc this year? Did you guys do that yet? No, not yet. Okay. All this means, it's just like a big Greek E. All it means is we're going to add up a bunch of things. It's like a summation thing. So I'll show you what we're doing. And you're not going to have to do this by hand every time. The calculator will do it. But you do need to understand like what the calculator is doing. So for the first category, the observed was 17. The expected was 20. That gets squared, and I divide by 20 because that was the expected. So the way this works is we're going to do this 5 times, one for each box, and we're going to add those up. The bigger the number I get when I add them all up, I'm going to stop talking because you guys are just adding them all up. You're just doing it. Fine, let's just do it. Nobody's listening to me anyways. So I'll just do the next ones. The next actual is 20, or observed is 20, and the expected is 20. So like, what's the value of this whole thing going to be right here? 0, because there was 0 difference between what we got and what we expected. Again, you're not going to have to write these out every time, but I want you to see what's happening. And we're not going to calculate it. I mean, we are going to calculate it, but not like adding those up. We're going to have to calculate it. So yeah, grab a calculator. So, think about like what would make I'm going to add all these up. Think about what would make that really big compared to what would make that really small. if these were all 20s, like the observed are 20, or the expected are all 20s, if my observed were all also 20s, like I just got straight 20, I got exactly what they expected, I'd have 5 of these, right? If I added up 5 of those, what would I get? I'd get 0. That means there was 0 difference between what was expected and what was, so I'm not going to reject their claim because like there's no difference. You start rejecting as these numbers get bigger and bigger and bigger. So think about how would that become a bigger number? Well, the further that is away from 20, then I'm going to square it, and I'm going to divide by 20, I know, but I'm just going to start, like if that were 17, you're going to get a certain number. If that were 10, would you get a bigger number or a smaller number? You get bigger, because 10 minus 20 is bigger, and you're going to square it anyway, so that like positive, negative doesn't matter. So the further we are away from 20 in each of these cases, the bigger number we're going to get. We're going to add up these numbers. The bigger number we get at the end, the more likely we are to reject, because we had like a big difference between observed and expected. So what's actually happening is this would be like 3 squared, negative 3 squared. So 9/20ths plus 0 plus 25/20ths. So you're just adding these things up. But in the calculator do it for you. So go stat, calc, tests, and then there's 2 chi-squareds. There's a chi-squared and a chi-squared GOF. We're doing the GOF, goodness of fit. So what it's asking, and I have to go back and do this still, but it's going to tell you, like, hey, you need to put the observed numbers in L1, and you need to put the expected values in L2. So let's go back and do that. Observed is L1, expected is L2. So stat, edit. So in L1, I'm putting the actual values. And then in L2, I put the expected, the ones that I had in parentheses. And then like go back and do the chi-square goodness of fit. Now you can run it. I was just showing you like where you needed to put things. So now go back to GOF. And you put things where it wanted. You put the observed in L1, you put the expected in L2. The degrees of freedom is the number of categories minus 1. There's 5 categories, right? And they're numbers right now, but they could just easily be like red, green, blue, yellow, brown, whatever. 5 categories, so degrees of freedom is 4. And then if you calculate, it will give you the total, it gives you 3 things. So this is the total of all those, like the 5 fractions that we had, 3.4. That gives you a p-value, which I'll show you how to find that if the calculator did it for you, degrees of freedom. And then this is the contribution, so I just want to talk about that for a second. If you scroll to the right, you'll see there's 5 numbers there. Those are the 5 numbers that were being added up. So, like this one right here, this would be -3, -3 squared is 9, now number 20 is 0.45, that's why that first number is 0.45. Second number is a 0 because we had 20 and 20, right, so there's 0 difference. So if you were to add up like 0.45 plus 0 plus 1.25 plus 1.25 plus 0.45, what would you get? Don't do it, but what would you get? 3.4. That's what this is. This is the sum of all these. And this is just breaking down like how much we're getting from which part. So I'll write that down. So your chi-squared is 3.4. Degrees of freedom is 4. And then we need a p-value. Like we know the p-value, but we gotta pretend we don't know the p-value. Just like we had normal CDF when we were dealing with proportions. When we were doing means, we had T-CDF. So there's a chi-squared CDF also. So you're gonna go chi-squared CDF. But this is a little different. If you look at a graph of chi-squared, it is always right skewed. And we are looking for so our chi-squared value is 3.4, I don't know, let's say it's right there. You are always, always, always going to the right of these. So there's no like greater than, less than, not equal. It's always gonna be to the right of your chi-squared value. So chi-squared CDF, your lower bound would be that 3.4. Your upper bound would be 99999. If you try to put that in the calculator, it's going to give you an error because it wants the degrees of freedom also. So that's another way you could put degrees of freedom. Like if you didn't put this over here, you could just put like a DF right there, and then I think it's the same thing. So we know it's supposed to be 0.493. Let's actually like do it so we can, and that's equals P value. So let's like do chi-squared CDF though to make sure that we get that same thing. So second distributions, like the same way, just like you're looking for normal CDF or TCDF. If you scroll down to number 8, it's chi-squared CDF. And then I'm going to put in, my lower was 3.4, my upper was 9999, 4 degrees of freedom. And I'm just verifying that I get the same thing, make it better. So, I'm just like showing you how you jump through the hoop to show that you know how to do it. But this could also very easily be like a multiple choice deal. So again, like the further these were away from what we expected, the further we are to the right, and the more we go to the right, the more likely we are to reject. But this is not really very far to the right. So, I didn't give you an alpha, so what do we say? 0.05, so the p-value is way bigger, right? So since p-value is greater than alpha, because remember this, we failed to reject HO, is or is not statistically significant? It's not. Do suspect, no, sorry, we do not suspect AJ is true. So I know you learned this 10 seconds ago and process. But are there any questions I can answer at this point? Like I know you don't fully understand, I'm not saying that, but I think I can clarify. Okay. Let's do I want to do another example actually. Before we do a template. So we're going to do a chi-squared GOF. Bring me your take-home test, please. There's a pile, start a pile on the chessboard. I said on the chessboard. copying this off like an old AP. We're doing mice from a lab. The ratio should of red eyes to brown eyes to pink eyes to blue eyes is supposed to be 9 to 3 to 3 to 1. So that'll make the expected part a little more challenging. And what we got was 119, 48, 32, and 13. So I want to see how well our data that we collected from these mice matches this proportion. And I can't even really tell, man, I can tell by looking, but so like that number should be 3 times bigger than that number, right? So we would expect it to be 39 if this number is right. These two should be pretty much the same. Should be the same because it's 3 to 3. That number should be like 3 times bigger than that and like 9 times bigger than that. And then we're not going to get that exact, but that's the idea. That's what we're trying to see if it fits or not. So HO, I would say the claimed distribution of eye color is correct. And HA at least one claim is incorrect. Does that make sense, the idea? We're trying to like see if it fits or not. So our conditions in this are I or up. I is independence. The problem does not give me the total, so I gotta add these things. What is it? 212, thanks. So 212 is less than 10% of, these are mice, all mice. I guess maybe all mice with eyes, but I'm not gonna write that. Sure. R is randomness, which wasn't really stated, because I'm being kind of half-assed about I'm giving a problem, so let's just say assume my sense. And then L is large counts. So each expected value is supposed to be greater than or equal to 5, which we will show in a second. Chart. Jackson, you can just take it back there. That's easy. You can just take it. Alright, so I'm going to have red, brown, pink, blue. I'm putting observed and expected. Bottom part's just like a key, so like I'm telling the person reading it, hey, this is what it means. The number that's not in parentheses is the observed, and the number that is in the parentheses is the expected. The observed numbers I can just write down. The expecteds are a little more difficult with this kind of problem. So one of I'm looking for is I wanna know the expected number of reds, let's say. I mean, starting with reds. What fraction of the mice would you expect to have red eyes? Don't say it louder. What fraction? 9/16. So what we're getting at is if I added all these up, there's 16 of them. Out of every 16, 9 of them should have red. So 3/16 to be brown, 3/16 to be pink, and 1/16 to be blue. Does that make sense? I'm getting that 32. Okay. So that number is going to be 9/16 times the total, which was 212. And you don't have, this is like my scratch work, like you don't have to show this part. I'm just doing it for teaching purposes. But go ahead and figure out the expected for all 4 of those. So this is 9/16 times 212, I got 119.25. So that's like really close to what we expected. So right now I'm already thinking this is probably gonna be a pretty small chi-squared, which means we're probably not gonna reject. Well, let's see. This would be 3/16 times 212, so I got 39.75. It's a little further away. This is going to be the same value, right? Isn't this also 3/16 times 212? So that's also 39.75. I regret not making my parentheses larger. And then what fraction will be here? 1/16, right? So 1/16 times 212, so 13.25. Those are all pretty, I mean, these two are very close, and these two are still pretty good. So that is like showing our expected values greater than or equal to 5, and just kind of organizing what we're about to do. So now I'm just going to say chi-squared equals the sum, that's what this E means, of O minus E squared over E. And I'm not going to write out the 5 like fractions that I wrote out in the last one. I don't have to do that. I was just doing that to like help you guys understand what was going on. So really all you got to write is the chi-squared formula says I'm supposed to add up, that's what this means, all of the observed minus expected squares over expected. And then I'm just going to my calculator. My calculator is going to basically do the rest of the whole thing. So remember, you're going to put the observed in L1, expected in L2. Remember, if you go up to the top, like if you go to L1 and hit clear enter, it'll clear the row for you. Don't hit delete. Delete means destroy. Don't destroy it. So observed L1, expected L2. And then go stat tests. And if you scroll down to GOF tests, again, there's 2 chi-squareds, but this is specifically a goodness of fit. And I put them where they wanted. Observed is an L1, expected is an L2. How many degrees of freedom are in this guy? 3. So there's 4 categories. You subtract 1 for the degrees of freedom. Then I can go ahead and calculate. Gives me chi-squared, gives me the p-value. Let me ask you this. What is the contribution of Brown to the chi-squared statistic? What is Brown's contribution to the chi-squared statistic? Let's start with this. What is Red's contribution? Red's contribution, because we put in, didn't we go red first? Red, brown, pink, blue. So that number is Red's contribution. Didn't you say like .005?
Yeah. There's more to it.
makes sense because they were like right next to each other, weren't they? Yeah. So that first contribution, you're right, my bad, is like 0.000524. The next one's 1.71. This is 1.51. The last one's probably super small too, right? Yes, 0.0047. Okay. So the total chi-squared is 3.229. 8.85. And I don't have to write out all those, so that saves a lot of time, right? I was just doing that to explain. I'm going to pretend I don't know the p-value yet. And I'm going to type into my calculator chi-squared CDF. I already know it. So remember, it's always to the right on these. And it's going to also ask for the degrees of freedom. Make sure you put that at the ends. And then if I were to type that in, I would get 0.3577, and I know that because it just told me that. But if you want to type it in to verify, that's cool too. Okay, so that's the p-value, so make sure you label that, equals p-value. Then I'm going to do my little graph and a conclusion. So chi-squared is always skewed to the right. That may be the best skewed right I've ever done. Look at that. That is cool. Nobody cares. I get that. 3.29 is somewhere, or 3.229 is somewhere over there. The shaded area is the p-value. It's the 0.3577. And then we can do our conclusion. So I didn't give you alpha, right? So assume, maybe we should write that up here somewhere. Alpha is 0.05. So the p-value is bigger. So since p-value is greater than alpha, fail to reject HO. Are you guys getting what I'm getting? Like your numbers are matching, everything's going? Okay. Test is not statistically significant. And we do not suspect HA. We do not suspect HA to be true. Questions anywhere on that one I can go through? Alright, I'm going to do it a little different this time, because normally we would do the template. I already did it a little different, I guess. I'm going to give you one to try on your own before we do a template, because I think this part gets tricky for some people. I know that part gets tricky for some people. So I'm just going to make another one up, and we'll do that. So let's say, teachers used to do this when I was at Michigan, and it's just fucking evil. They decided, like pre-decided, 10% of the people in this class are going to get an A. Let's say 30% are going to, I don't know what the numbers were, but it's just cruel to be like, even if everyone in the class knows every single thing I teach, only 10% of you are getting A's. 30% B's, let's say 40% C's, 10% D's, and then 10% F's. So that's this professor's claim. Then I look at their grades over a course of years, and I see, so maybe it's 1,000 people. So how many would I expect to get A's? Be 100, it's 10% of 100. Let's say it's 80. Yeah, this is hard to do. Velocity observed. That's your expected. Don't forget title. Do you have a specific order that you'd like her to hang them to you in? Or when you said mind, I thought you said that you had a mind first, which would have been really fun. Let's say alpha is 0.05 and it is an SRS. And they've been teaching for a very long time and their classes are very large. P-value is very small. So I have a question for you at the end too. Which grade contributed most to the chi-square? So I want you to do the thing, check it, and then try to answer that question. Does that pile look like there's 25 tests? Looks like there's like 10. Scary. Is that big enough, like in the back, can you see it to check? It's like that marker has an eraser on the other side. It's like a pencil. Flip it over
It's
to.
not working very well.
Looks to me like it is.
Well, normally it works better, but I don't know, something with this one.
It's a defective marker.
Yeah, it doesn't like move very well.
Alright, how many again, what I'm getting? Questions on anything I can address, go through, clarify? I wanna talk about that last question for a second. Lily, do you have a question, or you were just like, I got one? Okay.
I just,
You just let it hang there for a while, I wasn't sure. So, which one contributes the most to the chi-squared statistic? That's trying to get you to look at those values on the bottom and see which one's the biggest. So again, these are the contributions from each of the 5 categories. So the first contribution's 4, so far that's the biggest. Then I got 1.33, and then I got 16, then I got 64, so the 4th category is the biggest. So D is contributing the most. Does that make sense, that why D is contributing the most, or how we talk? Anybody, frickin' nod your head, yes or no? Okay, thank you,
Yes.
thank you. No one said anything, we just stared at me. Alright. Did you guys do it?
I said.
When I say nobody, I mean like not nearly many people as I wanted. Not actually nobody. Like, I'm hoping for like 10. I get 1 or 2. That's all for today. We'll do a template tomorrow. But if you screw it, yeah. Yeah. Hold on. Are there any other tests? More than I thought, actually. Doesn't have to be far. It's like it's a decent amount of work. How long did this guy take you? How long did this guy take you? How long did this take you guys?
Yeah.
Couple hours?
2 hours. 2 hours once I get work done.
Like it doesn't, they don't, doesn't have to be tomorrow.
It was 12:30 a.m. to 2:30.
I didn't mind like on Thursday. I just sat with it.
I got done with mine almost 6 hours ago.
I know, that's like the somewhat interesting part, right?
I was like, I know it's like a guide, so I did that, and then I was like, okay, I'll just.
I have my first
Nice.
so I just would find out what it was and find out.
I used my last two, I used my program part and then my seventh one, and then I was just like,
I wrote my note card. I used the same note card for both tests. I used to erase it.
because I had to,
I still haven't done
That's all I have to say about that.
No. That's like a free. Oh no, I've done the fast one, but I haven't turned it in. It's actually been fun.
It's been so long. We should all go to the.
we should do it tomorrow morning. Tomorrow morning.
For sure. We'll put it off till tomorrow.
Look at me like that. Don't put me under news, please. I do not want to be put on the news, please. I don't want any footage of me out there, please.
YouTube, see you.